Theory and analysis of two-way transmission line. See, suppose this is a transmission line, and here it is connected some voltage source Vs, and current from that voltage source is Is. And here it load ZL is a current flow through load, and ZL is load impedance. If this carries a charge density of plus rho L, this carries a charge density of minus rho L. Then in the middle, magnetic flux equal to 2 pi m because using right hand rule it into the paper, and it is also into the paper 2 pi m, and we know flux directly proportional to current, so flux equal to Li. L is inductance equal to flux per current, Henry. This is similar to one wire is carrying current into the paper and another wire is carrying current out of the paper, and distance between them is 2d. Equivalent circuit of transmission line. See, every transmission line can be represented as this, because transmission line has some resistance that is represented by had. It stores some energy, so series inductance L is used. This is series resistance, and between two wires there are conductors, and between them dielectric is present, that is capacitance. Series shunt conductance is there, and G is for every shunt conductance has some loss, every capacitor has some loss, that is represented by shunt conductance. Shunt capacitance is C is shunt capacitance, G is shunt conductance. This can be represented as Z. Series impedance, this can be written as shunt admittance, ZY. Secondary constants of transmission line. Secondary, first is a characteristic impedance. Characteristic impedance is defined as characteristic impedance under root Z by Y. Z0 equal to under root R plus J omega L, Y equal to G plus J omega C. So this is propagation constant P is defined as P equal to under root JY, R plus J omega L, G plus J omega C. So evaluation of primary constants from the given secondary constants, we can just modify. We have Z0 equal to under root Z by Y, P equal to ZY. Then multiplying P Z0 we get Z. So Z equal to P Z0. P by Z0 equal to Y. P by Z0 equal to Y. Y equal to P by Z0. So G equal to real part of P by Z0. C equal to imaginary part of real P by Z0. R equal to real part of P Z0. L equal to imaginary part of P Z0. Voltage and current equations at any position on lossy transmission line. See, take this as a lossy transmission line. Its ending or input end or generator end Vs and Is. This is a receiving end or output end or load end. Take at a distance of x, we find the voltage and current equations, and length of the transmission line is L. So from end this distance will be L minus x, and Z0 is characteristic impedance of this transmission line. This can be written as same. Here PQ is considered small section ds, that PQ can be considered as ZY. Potential drop or decrease in voltage dV by dx equal to Iz. Decrease or change in current equal to di minus di by dx equal to Vy. This is the wave equations for voltage and current. D square V by dx square equal to rho square V, D square I by dx square equal to rho square I. These are just similar to analogous to electric field magnetic field equations, that is Helmholtz wave equations. And here while simplification, this is very important. E power px equal to cos hpx plus sin hpx, e power minus px equal to cos hpx minus sin hpx. Then we get Equations, voltage and current equations at any position x on lossy transmission line from x is from starting end. V equal to VR cos HPL minus x plus IR Z0 sin HPL minus x. I equal to IR cos HPL minus x plus VR by Z0 sin HPL minus x. Substituting L minus x as x dash. X dash is from receiving end. Voltage and current equations at any position x dash from receiving end. Vx dash equal to VR cos HP x dash plus IR Z0 sin HP x dash. Ix dash equal to IR cos HP x dash plus VR by Z0 sin HP x dash. At sending end x equal to 0, x dash equal to L. At receiving end x equal to L, x dash equal to 0. Impedance at any position on lossy transmission line. Zx equal to Vx dash by Ix dash. We know Z equal to V by I. Impedance at position x at any position x on lossy transmission line is given by Zx dash equal to Z0 plus Zr tan HP x dash by under root Z0 Zr tan HP x dash. Just remember, so Zx dash is remembered as right Z0 and below that again write Z0 Zr tan HP x dash into Zr plus Z0 HP dash. Z0 is there, here should be Zr. At sending end x dash equal to L, then Vx dash is Vs, Ix dash is Is. So Zx dash will be equal to Vs by Is equal to Zn. That is input impedance of lossy transmission line. Zn equal to Z0 Zr plus Z0 tan HPL by Z0 Zr tan HPL. On lossy transmission line we have alpha and beta. Okay, no need to remember this because never questions will be asked to find direct alpha and beta. And next we learn about line distortion. What is line distortion? Line distortion can be classified into two types. First is frequency distortion, second is phase or delay distortion. It is similar to distortionless transmission in signals and systems we study. For a signal to be distortionless transmission, magnitude is constant with respect to frequency and phase should be linear with respect to frequency. It is just same as here. And to eliminate frequency distortion, alpha must be independent of frequency. If you want to eliminate frequency distortion, make alpha independent of frequency. If you want to eliminate beta distortion, make beta must be linear with the frequency. That is similar here. If you want to make alpha, make gain independent of frequency. Here make alpha independent of frequency. Here make phase with linear with the frequency. Here make phase or delay beta, to eliminate phase or delay distortion, make beta linear with the frequency. Same, it is analogous in signals and systems, and here in transmission lines, line distortion also. Line which eliminates both frequency distortion and delay distortion is said to be distortionless transmission line. What is distortionless transmission line? Which eliminates both frequency distortion and delay distortion or phase distortion. For frequency distortion, alpha must be independent of frequency. For delay distortion, to remove, beta must be linear with the frequency. So to get a condition for distortionless transmission, just equate beta expression, second term of beta expression under radical to something and do calculations, but calculations are nothing. Just remember the formula Lg equal to Rc. Just remember Lg brand and Rc circuit, that is condition for distortionless transmission line. Just remember that. What is the condition for distortionless transmission? Lg equal to Rc. And okay, now we will derive propagation constant for a distortionless transmission line. We have propagation constant P equal to under root R plus j omega L plus G plus j omega C. And here taking L common, here taking C common, we have LC, and taking LC out of root, under root LC R plus L or j omega or G plus or under root LC G plus C j omega, because R by L is replaced with G by C, or G by C is replaced with R by L, so we have this roots get cancelled here. So R by L under root L by C plus j omega under root L by C. Beta equal to omega under root LC, alpha equal to R by Z naught, alpha equal to Z by Z Z naught. Or still remember in distortionless transmission line, alpha equal to R by Z naught or z into z naught, beta equal to omega under root LC, omega under root LC, Vp equal to 1 by under root LC. Z naught equal to characteristic impedance under root Z by Y, Z equal to R plus J omega L, Y equal to G plus J omega C. And same taking L common and here taking C common, we get these terms cancel because they are equal. So Z naught equal to under root L by C equal to R, that is purely resistance. Characteristic impedance of distortionless transmission is purely resistance. What is that? Z naught equal to under root L by C. Next we have lossless transmission line. Lossless transmission line in which components which absorb power must be zero, that is resistances and conductance are the one which absorbs power, so they must, if they are zero, that is called as lossless transmission line. So P equal to alpha plus J B equal to under root 0 plus J omega L 0 into 0 plus J omega C. So P equal to J omega LC. It is similar to perfect dielectric medium. We have in perfect dielectric medium also perfect dielectric medium gamma equal to J under root J omega epsilon mu epsilon under J omega under root mu into C, epsilon. Same here, perfect dielectric medium or lossless medium. So here at alpha equal to 0, beta equal to omega under root LC, P equal to JB, propagation constant equal to Z naught equal to under root L by C R naught. Matched line. A line on which there is no reflection is said to be matched transmission line. If there is no reflection, then it is said to be matched transmission line. And we have reflection coefficient K equal to ZR minus Z naught by ZR plus Z naught. If there is no reflection, that is K equal to 0, then K equal to 0. K equal to 0 means ZR equal to Z naught. So for matched line, ZR equal to Z naught. For matched line, ZR equal to Z naught. Substituting here ZR equal to Z naught, we get Zn equal to, this terms gets cancelled, Zn equal to Z naught. So first of all, for matched line there should not be reflection. For no reflection, K equal to 0. Then if K equal to, for K to be 0, ZR equal to ZR equal to Z naught. If you substitute that in the input impedance of characteristic transmission line, Z naught equal to ZR plus Z naught tan HPL by Z naught ZR tan HPL, we get Zn equal to Z naught. That is, condition for matched line is ZR equal to Z naught. That is, it should be terminated with its characteristic impedance. If a transmission line of any length L is terminated with the characteristic impedance, then Zn equal to Z naught. First condition is, that is, it should be terminated with the characteristic impedance. If it is terminated with the characteristic impedance, it is said to be matched line. Matched line means there is no reflection, and the input impedance is equal to characteristic impedance. For matched line there is no reflection and standing wave ratio is 1. Next we have short circuited line. What is short circuited line means? That load equal to 0, that is ZR equal to 0. If our short circuited line, we know current is maximum, voltage is minimum. Then if you measure Zn for short circuit line, that is indicated by ZSC. ZSC here, putting ZR equal to 0, we have ZSC equal to Z0 tan HPL, Z0 tan HPL. Open circuited line, impedance looking into input terminals of line, Zn equal to ZOC for open circuit. If they are open circuited means voltage is maximum, current is minimum, ZR is equal to infinity. So open circuited line equal to Z0 equal to Z0 cot HPL, Z0 equal to cot HPL, ZSC into ZOC equal to Z0 square. When we multiply ZSC, Z0 cot tan HPL, ZOC, Z0 cot HPL, tan cot are reciprocal to each other, so they get cancelled and we remember only Z0 square. So characteristic impedance of any line can be equal to under root Z short circuit impedance into open circuit impedance. If the line is lossless, we know ordinary alpha equal to 0 and beta P equal to JB only, and P equal to JB only. Substituting JSC equal to Z0 tan J beta L, ZOC equal to Z0 cot J beta L, and here we have one formula, sin Hx sin H Ix equal to I sin X, sin cos Hx cos H Ix equal to cos X. That is, hyperbolic functions are